All right, so we're gonna build an adder. We're gonna go from these relatively simple circuits to something that you can really imagine a computer needing to do, which is to add a bunch of numbers together. So we're gonna do this in two steps. I'm gonna build a 1-bit adder, and then I'm gonna show you how it generalizes to a 4-bit adder. So in the same way we went from a 1-bit compare for equality to a 4-bit compare for equality, we're gonna build this up a little bit slow. So here's the task. Please build for me a circuit that adds two 1-bit numbers. So again, remember we have to think in terms of bits. So I have two numbers. Each of them are 1 bit. So either it's a 0 or a 1, and I'm going to add that either to a 0 or a 1. Okay. All right. So we know what we have to do. Let's first start making sure that let's start by understanding that let's start by making sure that we understand how the 1-bit addition works. So here are my two bits I'm going to add, bit 1, bit 2, let's call that A and B, and let's just do the addition. So 0 plus 0, of course, is 0. 0 plus 1 is 1, and 1 plus 0 is 1. That's easy. All right, what's 1 plus 1? Well, let's see. So this is 1 and 1 in base 10. 1 plus 1 is 2. What is 2 in binary? It is 1, 0. So now we have already got a little bit of a problem, because here I only have one output, right? There was no carry. But here I have sort of two outputs. I have the sum, which is 0, but then there's like that carry, or I have 2 bits out, it's 1, 0. So maybe I have to think about this a little bit different. So carry, and here's a good place to think about what's going to come next. So eventually we're going to want to build a 4-bit and an 8-bit and a 16-bit adder. And to do that, we're definitely going to want to be able to carry digits, because when we stack two binary numbers on top of each other, we need to carry information to the left as we sum. So let's see. So initially I was thinking I would just have two inputs A and B and one output C, but maybe I should rethink that. Maybe the input should be two digits, A and B, and then possibly a carry. And again, this is all about thinking down the line a little bit. When I go from a 1-bit to a 2-bit to a 4-bit, I'm going to stack these down, and think about how you just add normal arithmetic. You add the digits in the column, but you potentially bring something over from the previous column. So let's think about the binary addition in terms of now having three inputs, A, B, and a possible carry. And again, that's going to allow us to generalize the circuit down the line. Okay. Now, of course, the output has to have more than just this. It has to have an output, which is what pushes down below the horizontal line, but also gets carried out. So now, even this 1-bit addition has already gotten a little complicated. We have 2 in plus a carry, that's 3 in. And then the output is, what is the sum, and then what is the carry over here? So we're going to have two outputs. All right, let's make sure we see what's all happening here. So let's imagine I want to sum. I have a 3-bit representation, and I want to sum them up. So let's first of all make sure this makes sense. So 1, 0, 1. Remember, this is 2 to the 0, 2 to the 1, 2 to the 2. So this is 4 plus 1, which is 5. This is 2 to the 0, which of course is just 1, and then 5 plus 1 is 6. So I'm going to add these two numbers up, and I better get 6. So let's start adding them up, and I want you to keep track of these 3 in and 2 out. Okay. All right. So here I have clearly 2 digits. What's the carry from the previous column? There is none. It's 0. It's implicitly there's a 0 up there because there's nothing there. All right. What's 1 plus 1? 2. What is 2? It is 1, 0. So there it is. I have 2 in plus an implicit carry of 0. And my output is, what do I carry to the next column? That's 1. And what do I bring down? That's 0. Okay, good. Now you can see my 3 inputs. I'm going to sum that carry from the previous column plus 0 plus 0. What is that? That's 1. So I bring the 0 down, and implicitly I'm bringing the 0 over to the next one. So, and then I've got 0 plus 1 plus 0, and of course that is 1. And of course, if I do the calculation here, that is 2 to the 2, 2 to the 1, 2 to the 0. So it's 4 plus 2, which is 6. Okay? So 2-bit addition, if we are eventually going to want to generalize this to 3, 4, 5, 6, 7, 8-bit addition, we now have 3 ins. What are the 2 digits you're summing plus a possible carry? And we have 2 outs. What comes down and what carries over to the next column? 3 in, 2 outs. Good. So look at how much work, by the way, we had to do just to establish what the input-output is. Okay? But this is sort of the hard part now. We've established what the problem is. We've established how to define it. And now we just have to start building a truth table, sub-expressions, expression circuitry. Okay, so I have three ins. I should maybe call this a carry in and a carry out. Yeah, so it's what's coming in and then what's going out. Okay, 3 in, 2 out. All right, good. Let's build a truth table. All right, truth table has 3 columns. If it has 3 columns, it has how many rows? 2 to the power 3, which is 8. And the way you populate it is simply by counting in binary from 0 to 8 minus 1, 7. So 0, 0, 0, 0, 0, 1, 0, 1, 0, etc., etc., etc. So here are my 8 rows associated with the 3 input columns. Those have to, again, enumerate every single possible pair of inputs. And now I have to tell you what is going to be the sum that comes down and the carry that goes over. So again, these are the 2 digits we're summing plus a possible carry. That's the carry in. This is the sum and the carry out. Okay, so now we've just got arithmetic. We're going to tell the computer what the answer is in the same way we did for the compare for equality. I'm going to do this, the addition for you, and then the circuitry is simply going to implement those rules. All right, let's start going through it. All right, 0 plus 0 plus 0 is 0, and there's 0 carry. Okay, that one's easy. What is 0 plus 0 plus 1? It's 1. So the 1 comes here. What's the carry out? 0. There's nothing to carry. There's no overflow. Okay, that's easy. Let's look at this one. So what's 0 plus 1 plus 0? Well, it's still 1. It's actually the same as this, right? I don't care what the order of these bits are. So no reason to do extra work here. Once I know there's only one 1 here, I know what the answer is. It's going to be 1, 0. Okay, so that one's easy now. This one, let's think about this. So this is 0 plus 1 plus 1. That's 2. So what is 2 in binary? Carry the 1, drop the 0. So that's going to be a 0 here. That's what comes down. And the 1 is what carries over to the next column. This one's easy. There's only one 1, so we know what the answer is, 1, 0. This one's easy. There's 2 1s here. The answer is 2. It's the same as that. 0 comes down, carry is 1. This one's easy, right? Work smart. We've already done the work. No reason to do the calculation. Now let's do the last one. 1 plus 1 plus 1 is, of course, 3. What is 3 in binary? It's 1, 1. Drop the 1, carry the 1. So now D is 1 and E is 1. Good. Now, really, truly, all the hard work is done. Now we got to just start turning the crank on sub-expressions, expressions, and circuitry. So I have 3 ins, 2 outs. I've established what the value of the sum and the carry out is for all possible inputs. And now let's start building up the sub-expressions. Okay, remember how the sub-expressions work. You treat each output column separately. The D and the E output column are completely independent of each other. We're going to identify wherever there's a 1, and then here, 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 and here. We're going to build a sub-expression using only and not. And then we're going to combine those sub-expressions using the OR operator. And then once we have the final expression, of course, we're going to draw some circuitry. So let's get started. All right, let's start with D. I've isolated 1, 2, 3, 4 1s here. So what is the sub-expression associated with this? Remember, you go back to the input variables. If it's a 1, you not. If it's a 0, you not it. If it's a 0, you not it. If it's a 1, you carry it over. So this sub-expression should be not A and not B and C. Okay, easy to do. But again, remember what you're doing. You're looking for an expression that is a 1 in one and only one situation, when A is 0, B is 0, and C is 1. So if I not these two, they turn to 1. That one's a 1. The only time that little sub-expression, which I'll draw right here, is 1, is in that little row right there. So not A, not B, and C. All right, let's do the next one. What is it? Not A, B, not C. Good. There it is right there. And then let's just do the last two. So this one is A, not B, and not C. And last one is easy, A, B, and C. Good. So there are my 4 sub-expressions corresponding to wherever there's a 1 on the output channel. I won't go through these again. I think we now know what the rule is. So this one, for example, is not A, B, and C, and these 3 you can derive from this right here. So I have 4 sub-expressions for D. I have 4 sub-expressions for E, and now I'm ready to put them together in an expression, and then we can draw the circuit. All right, so what's the expression? This sub-expression is 1 on this row only. The sub-expression is 1 on this row only, and so on and so forth. I want my output D to be a 1 if this is true, or this is true, or this is true, or this is true. So I simply OR all the sub-expressions together. Okay, there's the expression right there, super easy. This same thing. It's a 1 on this, 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 this. I want the OR of them, so I'm going to combine them with 3 OR gates. So now I have full-on expressions for D and E, and now I'm ready to build my 1-bit adder. Okay, so here is the 1-bit adder. Now in the past, what we have done is we've brought in the input from the far left and the output is on the right. I've done things a little bit differently. You can see down here the inputs are coming from the bottom up, and then the outputs are here. So again, A and B are the 2 inputs, C is the carry in, D is the sum, and E is the carry out. Okay, so the reason I've done it this way is I'm going to take these 3 inputs here and I'm going to drive them all the way to the top. And then notice the 3 NOT gates here. I'm peeling off the signal to the NOT gate. I'm going to drive those all the way up. And then I just feed the signal and the NOT of the signal into the AND gates, into the AND gates down here, and then into the OR gates. And the color coding here, of course, is the red corresponds to the D output, and the blue corresponds to the E output. The AND gates here are, of course, from the original sub-expression, and then the ORs, those 3 ORs, are summing them up to get the final output. And notice here that there's a fair amount of circuitry here. Even for this really simple 1-bit adder, you need a fair amount of circuitry. And so what we're going to talk about next is, what can we do to reduce that circuitry, and what happens as these things start to get more complicated, and also what happens when I try to build, for example, a 4-bit adder and suddenly I have to draw lots of these different gates and things get complicated very fast. We're going to see how we can think about these larger, more complex circuits. So we'll pick it up in a little bit. See you soon.